Fluorine, with the symbol F and atomic number 9, is the lightest member of the halogen group and appears as a pale yellow diatomic gas under standard conditions. Its high reactivity allows it to interact with almost every other element except for the light noble gases. In terms of abundance, fluorine ranks 24th in the universe and 13th within Earth's crust. The chief mineral source, fluorite, was named in 1529 based on its property of lowering the melting point of metal ores, deriving its name from the Latin word for flow. Approximately half of the mined fluorite is applied in steel making, while the remaining is transformed into hydrogen fluoride for the manufacture of organic fluorides or into cryolite for aluminium processing. The bond between carbon and fluorine is particularly strong, making organofluorine compounds resilient and useful in a wide variety of applications, including refrigerants, electrical insulation, nonstick coatings like PTFE, and pharmaceuticals such as those found in common medications. The fluoride ion, sourced from dissolved salts, has dental health benefits, widely utilized in products like toothpaste and in water treatment. The annual global revenue from fluorine-based chemicals exceeds billions of dollars. Most gaseous fluorocarbons act as greenhouse gases, with some, such as SF6, possessing extremely high warming potentials compared to carbon dioxide. The durability of the carbon-fluorine bond means that organofluorine compounds frequently persist in the environment. While mammals have no known need for fluorine in metabolism, some plants and marine sponges produce organofluorine toxins, which serve as a defense against being eaten. A fluorine atom contains 9 electrons, arranged so that it needs just one more to complete its outermost shell. The high effective nuclear charge felt by the outer electrons leads to a high energy requirement to remove one, second only to a few other elements, and gives fluorine the highest electronegativity of any element that reacts commonly. Its covalent radius is small, similar to oxygen and neon. Depending on the metal, some require powdering or higher temperatures for a reaction, and noble metals need pure fluorine gas at elevated temperatures. At room temperature, fluorine exists as a pale yellow gas with a sharp, biting odor detectable at minuscule concentrations. Cooling causes it to condense into a vivid yellow liquid, and even lower temperatures produce 2 distinct solid phases, beta and alpha fluorine, each with its own crystalline structure and properties. Fluorine occurs naturally as a single stable isotope. Its marked sensitivity to magnetic fields makes it useful in NMR and MRI technologies. Artificially produced radioactive isotopes of fluorine have fleeting half-lives, with the exception of one isotope used in medical imaging. Fluorine's cosmic presence is limited due to how stars produce elements, with most fluorine atoms quickly converted into oxygen or neon during stellar reactions. Yet mechanisms such as supernovae or stellar winds offer explanations for its persistence in the universe. Breakthroughs in materials and techniques finally allowed Moissan to isolate the element safely in 1886, a feat recognized by the Nobel Prize. The development of organofluorine chemistry significantly shaped modern materials and consumer products. Early use included hydrofluoric acid in glass etching, but by the 20th century, fluorinated refrigerants, PTFE, and related compounds found large-scale applications, permanently influencing daily life and modern manufacturing. Fluorine exhibits broad chemical versatility, forming compounds with metals, nonmetals, metalloids, and several noble gases. Its strong electron attraction leads to a preference for ionic bonds, while covalent bonds tend to be highly polar and typically singular. Chemically, fluorine nearly always adopts an oxidation state of -1, except in its elementary form, where its state is defined as 0. Rare intermediate or positive states exist only in extremely reactive or unstable species, most of which decompose rapidly at low temperatures. Predictions suggest a handful of exotic, more positively charged fluorine compounds could have stability under specific conditions. When reacting with metals, alkali monofluorides are notably soluble and ionic, sharing structural features with typical salt forms. Alkaline earth difluorides, apart from beryllium difluoride, which displays further covalent properties, are generally water insoluble. Many metals, especially among the rare earths, generate primarily ionic trifluorides. More structurally intricate bonding patterns emerge with compounds bearing 4 or more fluorine atoms per metal, such as tetrafluorides, some of which are high melting and ionic, while others form polymeric frameworks. Metal pentafluorides and hexafluorides are known for their volatility, unusual geometries, and often a marked tendency to form molecular or polymeric solids. Notably, rhenium forms a unique heptafluoride exhibiting a bipyramidal structure, while gold can create low-temperature complexes encompassing nearly neutral elemental fluorine within its molecular makeup. Metalloids and nonmetals of the p block generally form volatile, covalently bonded binary fluorides of varying reactivity. Some heavy nonmetals can surpass normal electron count limitations to give hypervalent fluorides. For example, boron trifluoride is planar and acts as a Lewis acid, while carbon tetrafluoride is almost inert despite its tetrahedral structure. Group analogues such as silicon and germanium tetrafluorides also behave as strong Lewis acids, but nitrogen trifluoride, unlike its heavier analogues, resists hydrolysis and does not act as a base. Among the more highly fluorinated compounds, antimony pentafluoride stands out as one of the strongest neutral Lewis acids after its gold counterpart. Chalcogens display a range of interesting fluorides. Oxygen can form an unstable difluoride, its only compound with a positive oxidation state. Tetra and hexafluorides of sulfur, selenium, and tellurium display increasing stability with lighter central atoms and more surrounding fluorine atoms, with sulfur hexafluoride recognized for its remarkable inertness. Halogens also create a range of fluorides such as mono, tri, and pentafluorides, but only iodine is confirmed to form a stable heptafluoride. Noble gases long resisted combination with other elements until advances in the 1960s showed that, under special conditions, xenon and at least a few heavier gases can be induced to form fluorides, including difluorides, tetrafluorides, and hexafluorides. Lighter noble gases largely remain unreactive, though a few fleeting compounds have been detected under extreme experimental conditions. In the realm of organofluorine chemistry, the carbon-fluorine bond is both remarkably strong and rare in nature, though widely exploited commercially. Perfluorocarbons, where all hydrogens are swapped for fluorines, show increased stability, become insoluble in most solvents, and react under ambient conditions only with the most vigorous reagents. Adding functional groups to these skeletons creates perfluorinated compounds, which often serve as surfactants or adhesives due to their combined stability and reactivity. Fluorosurfactants, for example, easily repel water and are far more effective than their hydrocarbon-based relatives. Fluoropolymers, such as polytetrafluoroethylene, PTFE, benefit from the same robust carbon-fluorine bonds, which grant them high stability and melting points. PTFE's high melting point makes it tough to process, so related polymers with substituted groups provide easier molding at the cost of some thermal stability. Many fluoropolymers find uses as coatings, electrical insulators, and chemical-resistant linings. Sulfur hexafluoride, prized for its dielectric properties and inertness, plays an important role in electrical transformers and circuit breakers. Rhenium and tungsten hexafluorides are significant in the electronics field, especially in the process of chemical vapor deposition. Tetrafluoromethane finds use in plasma etching, while nitrogen trifluoride is critical for cleaning equipment. In metallurgy, fluorine, primarily in the form of acid-grade fluorite, acid spar, is indispensable, notably as a flux in aluminum smelting and as an additive to adjust the properties of steels and other alloys. Hydrofluoric acid, mostly derived from this source, is necessary for glass etching, steel treatment, and alkane cracking processes. Organofluorine compounds take a significant share of fluorine demand. Halogenated refrigerants, previously dominated by chlorofluorocarbons, gave way to hydrochlorofluorocarbons and hydrofluorocarbons due to environmental restrictions. Efforts now focus on molecules with much lower global warming impact, including hydrofluoroolefins. Fluoropolymers dominate the polymer market by value and mass, with PTFE leading in uses ranging from electrical insulation to non-stick cookware and specialized fabrics. Expanded versions of PTFE serve in demanding filtration and membrane applications, while fluorinated ionomers, such as naphthalene, are central to fuel cells and chemical industry processes. Fluorosurfactants exist as a costly but effective subset, enabling water and stain resistance in fabrics. Their use is reserved for higher value products due to cost, despite their effectiveness.